Subscribe now.
So as you can see over here, in my previous tutorial, we talked about the various types of AM modulation. We talked about double sideband, of which I use a general equation for it. And then I also talked about the double sideband suppressed carrier, the single sideband suppressed carrier as well. And in this tutorial, I'm going to take the double sideband suppressed carrier, which is DSB modulation, to analyze it. Now let's kick it off. When we are doing an amplitude modulation, I drew the general phasor diagram over here. After everything, you are going to get from this equation AC, which is having a frequency omega c. And when I rewrite this, I can rewrite it as 2 pi fc. When I'm rewriting this, I'll do 2 pi fc plus 2 pi fm, of which I can factorize 2 pi out and get fc plus fm. When I'm doing this one here for the lower sideband, it's the same thing, 2 pi fc minus 2 pi fm, of which we are going to get 2 pi into bracket fc minus fm, which is the lower sideband. And I drew this diagram. So as you can see over here, this modulated wave has the information signal with the frequency fm at only the sidebands. I will also say that the sidebands is not anything like the band of frequencies, so as we have represented them with the phasor diagram. And this contain the power. And these ones are the lower and the higher frequency of the center of the carrier frequency. So you can observe that the transmission of this signal with the carrier frequency along with this two sideband, which is the lower and the upper sideband in addition, is what we call the double sideband full carrier, which is what the double sideband full carrier. Let me write it here, the double sideband full carrier. That, in fact, that is the general equation that I showed you over here. So you can also plot it as, instead of using the line that I use over here, the lines here, you can also represent them as a square wave. So now this is my lower sideband, and this is my upper sideband, and this is my FC. So this is my AC, the amplitude, and then this is also the amplitude of the lower sideband. So here is the LSB, and here be USB. So in explaining this is the double sideband full carrier. So the double sideband suppressed carrier, we will have only the two sidebands with the carrier being suppressed. And therefore the diagram, it's going to be like this way. So you can label it as FC minus FM, FC plus FM. Now, our carrier amplitude or our carrier parts aspect has been suppressed. And this is my USB, again, once again, and my LSB. So this is the DXB-XC, double sideband with suppressed carrier. Let's do mathematical analysis for this. In fact, let's use the definition first to get the various parameters that we want. So later on, we will come on to talk about the various modulators that we can use to generate a DSB. So in doing mathematical analysis, as the headline says, DSB double sideband suppressed carrier. Let's consider the same expressions, my message signal that I need, which is what? AM cos omega mt. My carrier signal, which is AC cos omega ct. Or you can change it to any other variable. Someone can choose to represent it as Vm cos omega mt, and then also represent it as Vc cos omega ct. They are all the same. So in some books, you will see them being represented like this. In some book, you see them being represented like this. So for the first one that we generated, we were adding this one. So when we want to suppress the carrier, what we need to do is to multiply the two, and we will suppress any other extra term. So in multiplying the two, we are going to get m of t multiplied by c of t, and then the resulting output is going to give us am ac cos omega mt cos omega ct. When you have this is simple to deal with. You can use trigonometric identities to help you with this. Let me rewrite it here. So ST is equal to AM AC, let's say AM AC cos omega mt cos omega ct. In using trigonometric identities, let's consider something here. Which of the trigonometric identities will help us generate this? Let's look into it. We have cos A plus B equal to cos A cos B minus sin A sin B. You also have cos A minus B to be equal to cos A cos B plus sin A sin B. When we add these two identities, we are going to, this one goes to 0, and now we are going to get 2 cos A cos B equal to cos A plus B plus cos A minus B. And dividing both sides by 2, we are going to get cos A cos B equal to cos A plus B plus cos A minus B over 2. Assuming that from this, our omega c or ct equal to A and our omega mt equal to B, we will arrive at an equation at cos omega ct cos omega mt to be equal to cos into brackets omega c plus omega m or t plus cos omega ct minus omega mt. You can factorize the t out, and don't forget that they are all over 2. So when we get something like this, remember that here we were having the amplitude to be AM AC, and therefore we can say that our S of t is equal to AM AC over 2 into bracket cos omega C plus omega M T plus cos omega C minus omega M T. But if you want a simplified version of this, you can see that your omega C equal to 2 pi Fc, my omega M equal to 2 pi Fm. And therefore, when we replace it, we are going to get some simplified versions like this with all components being exposed to be equal to cos 2 pi Fc plus 2 pi Fm, or T plus cos 2 pi Fc minus 2 pi Fm, or T. You can bring the 2 pi out, and then you are going to get something like cos into bracket 2 pi Fc plus Fm, and then plus cos into bracket 2 pi Fc minus Fm, or T. So this is what we are going to have, and you can see that the frequency component for the various sidebands, when you expand it, we are going to get AC AM over 2 cos into bracket 2 pi out Fc plus Fm, or T, plus AC AM over 2 cos Fc minus Fm, or T. So you can see that this is a double sideband, which is the upper sideband USB, excuse me, and the lower sideband LSB, with the carrier being suppressed. Therefore, the bandwidth or the frequency of my upper sideband is Fc plus Fm. The frequency of my lower sideband is Fc minus Fm. And therefore, my bandwidth is going to be upper sideband frequency minus the lower sideband frequency, which is equal to Fc plus Fm minus Fc minus Fm. At the end of the day, this Fc cancels this Fc, and we are going to get our bandwidth to be equal to 2Fm, which is the same as the one that we derived in my some of the previous video that I've done. So this is the bandwidth equation. As usual, we can also use this one to calculate the power of the double sideband suppressed carrier. And this is the amplitude of the sidebands. And as usual, power is equal to IV, of which we can also say that power is equal to V squared over R. Where, let's say, V is equal to VRMS, and VRMS is equal to VM root 2. So when I want my VM, which is the amplitude, I can say that my VM equal to VRMS over root 2. And when I place it there, I'll get my power for one sideband to be equal to VRMS over root 2 all squared and over R. And at the end of the day, I'm going to get power to be equal to V squared over 2R, where V is equal to VRMS. No, the V is the amplitude because I've replaced it over here. So where V is the amplitude, the VM. Now you have the power for this as a formula. Let's check the various sidebands. The upper sidebands, it's having the same amplitude as the lower sideband. And those amplitudes are AC, AM over 2. And therefore, we can say that when we substitute them into the power equation, we are going to get AC AM over 2 all squared over 2R. When your R, which is the resistance, is not being given, you take R to be equal to 1 doing your calculations. And therefore, when we simplify this, we are going to get the power is equal to AC squared AM squared over 4R times 2, of which we are going to get AC squared AM squared over 8R. But remember that this is for one sideband, which is either lower sideband or upper sideband, but they are all the same. So when you are being asked to find the total power of a double sideband suppressed carrier, it's equal to, which is the total P total, equal to P, the power of the lower sideband plus the power of the upper sideband. And therefore, my P total is going to be AC squared AM squared all over 8R plus AC squared AM squared all over 8R. Or you just take 1 and you multiply by 2. And at the end of the day, you are going to get AC squared AM squared all over 4R as your total power. But for a single sideband, the power is AC squared AM squared over 8R for double sideband suppressed carrier. So this is the total power requirement.